MCV4U1, Chapter 3, Applications of Derivatives, Session 9. In this session, we are working on Section 3.4, Optimization Problem in Economics and Science. In world of business, we are always looking for maximizing the profit or minimizing the cost. We deal with optimization problems. Let's work on the first example. A commuter train carries 2,000 passengers daily from a suburb to a big city. The cost of the ride is $7 per person, and market research shows that 40 fewer people would ride the train for each $10 cents increase in the fare, and 40 people would ride the train for each 10 cents decrease. If the capacity of the train is 2,600 passengers and carrying less than 1,600 passengers means cost exceeds revenue, what fare should the railway charge to get the largest possible revenue? We are looking for the maximizing of revenue. Revenue is number of passengers times fare per passenger. The fare price is 7 plus 0.1 times x. X could be a positive or negative number, and it is number of times that we increase or decrease the fare by 10 cents. And in this case, the number of passengers would be 2,000 minus 40x. Again, when x is negative, we say decrease in price, and when it is positive, increase in the fare. This means revenue is 7 plus 0.1x times 2,000 minus 40x. 2,000 minus 40x must be greater or equal than 1,600 and smaller or equal than 2,600, which is the same as saying x must be between negative 15 and 10. The capacity is 2,600, therefore 2,000 minus 40x must be less than capacity or equal to capacity, and the number of passengers should be greater or equal than 1,600 to have some profit. To find the maximum revenue when x is between negative 15 and 10, we follow the procedures for finding maximum minimum on a closed interval. We find the derivative of revenue function, which is negative 8x minus 80, set it to 0, and we see x is negative 10. We calculate the value of r at endpoints, negative 15 and 10, and also when x is negative 10. We see the maximum revenue is 14,400, and the fare should increase negative 10 times, and each time 10 cents. That means the fare should decrease by $1. Therefore, the fare of $6 and the number of passengers equals to 2,400 gives the maximum revenue of $14,400. Next example. A cylindrical chemical storage tank with capacity of 1,000 meters cubed is going to be constructed in a warehouse that is 12 meters by 15 meters with the height of 11 meters. The specification called for the base to be made of sheet steel that costs $100 per meter squared, the top made from the steel that costs $50 per meter squared, and the wall to be made of sheet steel that costs $80 per meter squared. Part A, determine whether it is possible for a tank of this capacity to fit in the warehouse. If it is possible, state the restriction on the radius. Part B, if fitting the tank in the warehouse is possible, determine the proportions that meet the condition and that minimize the cost of the steel construction. And do the calculation with 2 decimals. The radius of the tank cannot exceed 6 meters. And the maximum height is 11 meters, the dimensions of the storage, the warehouse. The volume using 6 and height 11 is more than 1,000, so making the tank is doable. There are limits on the radius. Obviously, the radius should be greater than 0 and smaller or equal than 6. Also, height must be 11. If we use height of 11, we'll see the volume is greater than 1,000 when R is greater or equal than 5.38. This means the restrictions on radius is R greater or equal than 5.38 and smaller or equal than 6. If the height is h meters and radius is r meters, then the cost of the base is the area of the base times $100. The cost of the top is area of the top, which is pi r squared, times $50. The cost of the walls, the wall of the tank is 2 pi RH times $80. Therefore, the cost of making the tank, if it is shown by C, is going to be 150 pi r squared plus 160 pi RH. We know the volume is 1,000. That means pi r squared H is 1,000, which means H equals 1,000 divided by pi r squared. We replace H by 1,000 divided by pi r squared to make C as a function of one variable r. This means CR equals 150 pi r squared plus 160,000 divided by r, and r must be greater or equal than 5.38 and smaller or equal than 6. To minimize the cost on a closed interval, we follow the algorithm. We find the derivative of the cost function, which is 2 times 150 pi r minus 160,000 divided by R2. Derivative of 1 over R is negative 1 over R2. If we set it to 0, we find R equals 5.54. We find the values of C at endpoints, 5.38 and 6, and at the root of the derivative, C at 5.54, and we see the minimum is 43,344. This means the minimal cost is approximately 43,344, and the radius of the tank is 5.54 meters, and the height is 10.37. Let's summarize this section. Profit, cost, and revenue are quantities whose rates of change are measured in terms of the number of units produced or sold. Economic situations usually involve minimizing cost or maximizing profit. To maximize revenue, we can use the revenue function. Revenue equals total revenue from sales times unit. Price per unit times X. Practical constraints as well as mathematical constraints should be considered. And once constraint on the model have been determined, which means the domain of the function is determined, apply the extreme value algorithm to find the maximum or minimum of the function. To understand this section better, next session we work on question number 1, number 2, number 3, number 4, number 6 from exercise 3.4 of the textbook. Thanks for watching.